So it seems that the meeting is now being streamed live on the YouTube as well.
Yeah, some of the people are catching up at the YouTube.
Yes.
Better.
Yeah, actually they can even join it, I think, the Zoom meeting if they have the meeting ID and the password. We do have some accommodation available on the Zoom meeting so that they can come in live in this. But otherwise, they can certainly continue to watch on the YouTube. But let me wish everybody there on the YouTube and welcome them to the course, welcome them once again, and suggest to them that in case they are interested and if they have the meeting ID and password, they can actually join on Zoom as well. This pandemic has given us the opportunity to do many things online, which is nice, but we really miss the face-to-face contact with students and participants, and it's a very unfortunate thing. So Vinay, do you think I should start? Sanjay?
Yeah, please.
Vinay?
Yes, we can start.
Yeah. All right. So good morning, everybody. And we are now on the last day of this short course, which Professor Sanjay Majumdar has kindly consented to offer for the Center for Atomic Molecular Optical Sciences and Technologies. And this is a joint initiative of the IIT Tirupati and the ISER Tirupati. And it's wonderful to have Sanjay give this course on quantum optics. There have been very effective tutorials as well. So thank you very much, Sanjay, once again for this. And thank you, Vinay, also for handling the session. Dr. Vinay Majeti will be conducting the session, and he will take care of the question answer session at the end of the class this morning. So Sanjay?
Yeah, so should I start?
Please.
Let me share my screen first.
Yes.
Let's see whether I can able to show this.
Yeah, it is good. You need to go full screen.
Yeah.
Yeah, I think you can do something. Yeah, this is best.
This is best.
Excellent. Perfect. Oh, I know where you are in the course. Yes, good. Thanks.
So
I missed yesterday's class, but from this slide, this slide helps me catch up. Thank you.
So, thank you. Good morning, everyone, for the last class. So you are able to follow some of the discussions which have been done here. Okay, we'll discuss those in our concluding mark. But let me catch up what we actually discussed in the last class. If you remember, in the last class, what we did, okay, so far we have done that quantization of the light. We have done the different tricks, how to make the quantizations, how to use the quantized light. Then we have talked about what is the statistics, okay. What is the beautiful application of the quantized light is that squeeze light. Now what we would like to see that some of the applications where actually we said that how this quantized light can be actually interact with the matter. So otherwise actually there's no fun in the game, isn't it? So unless you do some interaction, you do some manipulations, then only that physics will come out for physics. So what we said that when we confine this electromagnetic field, light, inside a small volume, we saw that light got quantized. And if we just space one quantum system, quantum matter like atom, molecule, or some quantum dot. So we have given different examples. Okay. So what you actually means what we discussed in the last class is that how these uh, coupled systems. Okay, coupled system is that this is a system with matter. That is what we are talking about here. A isolated atom inside the cavity, but it is not isolated because now we have a quantized electromagnetic field. Okay, so that it is no more isolated. So in presence of the electromagnetic field, still if we don't consider the coupling, so we'll have a composite basis state, okay, coming from the atom and the light, quantized light. And here we are taking the some simplest example of the two-level atoms, which is very, very useful for any kind of experiment which you do. And we have given example what are the possibility of the choice of the atoms which can be used for the two-level cases. So what we said actually, if you have a two-level atom, we having the ground state G and excited state E, and if we have the quantized electromagnetic field, which we are identifying as a zero state, one state, two state, telling that what is the number of population of the photon in that particular quantized electromagnetic state. So we'll get a set of bases. And as we have explained that depending upon the size of the trap or size of the confinement, size of the cavity, okay, what we can have that we can select what will be the frequency of the quantized electromagnetic field. So here omega will be the designated as the frequency for the electromagnetic field. And your resonance frequency between ground state and excited state, okay, is omega naught. So what we are shining, either we are shining blue tuned or red tuned, okay, what we discussed last class, okay, light, okay, to the atom, which is now having a two significant and distinct levels, okay. Now, once we have that, then what we are trying to do, okay. Before that, let me tell that whatever discussion on this chapter, what we are doing, it is taken from the famous books by Gindbach, Aspe, and Fevre, okay, Introduction to Quantum Optics, okay. So if you just look at the books, you also find it, okay, and I think I wish you should go through that book, okay. Anyhow, so what we found that we want to treat, okay, this coupling term, the atom field coupling term, as a perturbation, first order perturbation, and we want to see the physics or effect of this coupling, okay, in the basis of the uncoupled, okay, atom field, okay. So we have an uncoupled atom field, and we are trying to see this, okay, the interaction effect, that interaction between atom with the light effect, quantized light effect, okay. And what we found out in that basis, okay, so in that basis what we talked about, okay, that if we can shine the or if we can just think about that the size of the trap is such that omega is very close to omega naught, what we saw in the last class, we will have a doublet, okay. So zero photon with the excited state will be very or almost degenerate with the ground state with a single photon. So we'll have a doublet like that. Similarly, we'll have the doublet in the excited state, okay. And in this doublet basis form or doublet framework, we would be able to write our total Hamiltonian in this form, as we have discussed in last class. So what we just can do it, we can just diagonalize this, okay, and what we got it that eigenvalue of the systems, which is, as you see that this depends upon the detuning part, the delta, which is the difference between the resonance frequency and the frequency of the quantized light. And also it depends upon the Rabi frequency, which we discussed in the last class, okay. And so it depends upon both the quantities very much. And as we know that for any this kind of a combination where non-diagonal elements are non-zero. Okay, so what we could have a coupling between this uncoupled state, and the coupling will be giving you the effective new state, which is the eigenstate of the total Hamiltonian. So now we have eigenstate, new eigenstate psi plus n and psi minus n. N is designating as that whether how many number of photons are there, at least maximum number of photons available in the particular doublet. Okay, so it's like this case. I said that n is 1. So what we can write in cal, that we can write in terms of the cos theta, sin theta, and this combination between these two states. So superposition of the state. So we'll get two states, and we'll get a corresponding to energies. And according to that, what we see that these two new eigen energies, okay, or eigen values actually got splitted compared to the uncoupled one, okay, from the mean value. And here the tan theta is highly dependent on the tan theta is giving a mixing, highly dependent on the coupling between the states, okay, the electric dipole radio frequency, okay, and also depends upon delta. As we said that if delta is very high, okay, that means that if your quantized light frequency is very, very smaller compared to the resonant light, you don't expect any kind of mixing like that. You will have that two different, that uncoupled state will be disjoint, okay. And what would happen that if delta is very, very small, that means you are close to the resonance frequency, okay, then what would happen? We expect the very good superposition between these two. And so it depends upon the how strong the coupling, okay, between the atom and field, which actually comes from their Rabi frequency. So what we showed in the last class that we could get depending upon the delta equal to 0, which is almost close to the resonance frequency, okay, we could get that maximally entangled states, okay. So this was discussed for theta n equal to pi by 4, we will get that maximally entangled states. And then what we also discussed that how the variations of this mixing or superposition depends on delta. And I see that as I explained also that if delta is very large, we'll get disjoint uncoupled state. And once the delta is close to the 0, we'll get very good coupling or entangled state or correlated state. We can define in a different nomenclatures. Okay. Well, okay. So we have now this framework. And this is known as actually Jaynes-Cummings model, which we discussed in the last class with the references which we talked about. And today, what we'll do that we'll just go beyond that. Okay, what would happen that, so let's start with that. Okay, you have an empty cavity, that confined space you can think about, nothing is there, no field is there, only you have atom. Okay, so if you just think about that, you have an atom, okay, and that atom, what you did actually, you somehow make it excited with the laser, and that electron is in excited state. Okay, so what you do actually, you bring the excited atom from outside and just place it here. You can think about, and you make this cavity so that no field is available. Okay, so it's a simplest consideration, which is very difficult to achieve, but it will give some kind of idea which we can actually work with, okay, in the subsequent slide. Okay, so if you just see that, so you have that cavity mode, you make it such that okay, it is at the resonance frequency. That means what you can say that you have got this size of the cavity such that omega and omega naught is the same. That means delta is 0. Okay, so in that case, what is our initial state? Initial state is nothing but, okay, your E to the 0. There is no photon available. Okay, and electron is in excited state. As we have seen that, we can write this in terms of the modified or dressed state, okay, which is the eigenstate of the complete Hamiltonian. So if we write this one, okay, in terms of complete Hamiltonian, then we can say that after time t, if you want to observe the state, what we can do that, as we know that the psi plus and psi minus, they are the eigenstates of the complete Hamiltonian. So they are actually stationary states. So we can evolve them in a time with the proper coefficients. So what we did just exactly that. We evolved them with the proper unitary operator, okay, and we got that new superposition state, okay, in terms of the psi plus and psi minus, okay. And this is nothing but E plus and E minus, which we know in the last slide that how it can be calculated using the detuning part, which is we are telling it 0. Okay, you remember detuning is so using detuning and that coupling between atom and light. So now what you have that because you have started with the 0 photon, there's no photon was there, okay, and at t equal to 0 you have that this atom is in excited state, and we are observing this one. So now let us see that what is E plus and E minus in this case, and you know that here that we got this expression for the E plus and E minus, and here delta is 0. And if you consider that these two states are, we are just talking about G1 and E0, that means that N is 1. So we will have H cross omega only, and delta part is 0. And this will be just half of omega 1. And omega 1 is nothing but your radio frequency, which is giving you coupling. Okay. So what you got it here, that you could write this one, you can ask you to work it out very simple, that since that you have n equal to 1, e power minus I omega t will come out, and you will have that two different terms which you can write together in terms of the basis G1 and E0, which are the basis for the doublet here, and there will be sine function and cosine function. Right? So once we get this one, then we can say that, okay, we started with the excited state, okay, the electron in the excited state or atom in the excited state. What is the probability that the atom will be found out in the excited state in the later in time? So that if you want to find that state or atom will be in excited state and later in time, okay, so we can find out that probability. Okay, that is nothing but your this cost function, okay, and which is dependent only on the radio frequency. Okay, so it just depends on the radio frequency, and if you want to find the if you want to see the plot of this, okay, what would happen that this is the thing you can just consider n equal to 1. So you started with the probability that atom was in excited state at t equal to 0. Subsequently, once t is actually increasing, what would happen that your this cost function will reduce the value, and what would happen that the other functions, what is that probability to find the atom or electron in the ground state will increase with the expense of the probability of the finding the particle or electron in the excited state, and you will get some kind of oscillations. Okay, so you saw that there is some kind of oscillation, you got it, of the probability. So that what would happen that you are now see that if you have an empty cavity and keeping your one atom which is in excited state, you see that over time that electron will just hopping in that ground state and comes down, hopping ground state. So it is actually oscillating between the ground state and excited states. Okay, so this kind of oscillation which you see, it's known as a Rabi oscillation. Okay, so what we have learned so far that from this expression that the oscillatory evolution between these two atomic levels inside this cavity, so which is at the resonance mode, okay, so that is totally dependent upon that this is dependent upon your radio frequency, but this is quite totally different compared to if you just keep a atom in a free space, okay, and allow them to decay monotonically. Okay, so that is totally different. So you will have that excited state will decay and it will go to ground state and it will not comes back. So that is a big advantage that confining the atom inside a cavity. Okay, you can control this atom now. You see that. So you are able to control the atoms at different levels. Okay, and you can control using the Rabi oscillation. So this Rabi oscillation is arising because we are choosing now, okay, to discrete state, okay, coupling between that. And what would happen that there will be periodic energy exchange between this atom and cavity. So that's why you see that once the decay is happened, again it revives and again it decays. So what would happen, that electron can go from the excited to ground state and ground state to back. Okay, excited state. But in case of the free space, okay, what would happen, that this spontaneous emission which we are talking about, that will not be coupling between the two discrete states. It will coupling because we have already an excited state, which is discrete state, and with a continuum. So that's why you have the spontaneous decay kind of profile, okay, in the probability, okay, as you see it here. So what you just understood, I believe, that you just saw that this one is a Rabi oscillation where actually one photon is actually emitted and which actually takes place between these two states. Okay, so making the electron hopping from the ground to excited ground like this. So since it was started with a vacuum, okay, we can also say that it's a vacuum Rabi oscillation. Some people say it is one photon oscillation. So now if I just go further from one photon, which is was zero photon, okay, where cavity was totally empty, okay, and that we just say that cavity mode is actually resonant to the resonance mode of the atoms which was chosen. That means that frequency omega and omega naught are same. That means delta is 0. But if delta is not 0, what would happen? If delta is not 0, what you see that I am not calculating, but I can just tell you from this expression which you have got. Now delta is no more 0. Okay, so now delta is no more 0. Okay, and you get, this is the probability. So PB is for excited state. Okay, so it will be E. Okay, so what you see that is 1 minus some quantities which depends upon your Rabi frequency. Also that the detuning part, and there is a sinusoidal part. Now you see the interesting fact. When you make the detuning is very, very large compared to the Rabi frequency, what you see in the prefactor here, that this denominator will be very large compared to the numerator, and this will turn out to be 0. So the probability will be very close to 1. And that says that if you can make that your frequency of the quantized light such that it is far away from the resonance frequency, then what would happen? You will be able to keep the electron in the excited state over large time. So that means you will not be able to allow the electron to decay. And what you will find that electron is finding the electron in the excited state is almost constant, like 1. So which is a novel approach or novel actual finding, that now in general what happens if you have the atoms, we see that it will decay. Atom is the excited atom. It will decay to the ground state and we will have a spontaneous emission. But here we are just stopping the spontaneous emission by choosing that atom inside gravity, and we are making that cavity, and we are making the cavity such that the delta is very, very large compared to the omega 1. Okay, that is your Rabi frequency, and using that technique, if you can make, so experimentalists can hold the atom in excited state over a long time. And that is very much important for the quantum experiment, because you want to keep the system, whatever it is, for a long time, either in excited state or in ground state for a long time. Okay, so you want more coherence times for the system. Okay, so that is a high probability to keep the system in the excited states. Okay, so that so what would happen that, so here it is, cavity is far from resonance, as I said, so there is no spontaneous decay, and this can be achieved, okay, also in practical cases, like some of the interesting cases where actually an atom inside a medium of photonic band gap. Okay. So if you make the photonic band gap at its resonance frequency, then you will see that this kind of applications, okay, you will be able to do it. And this is the one of the paper soon after this was discussed, okay, the paper written 1987 in PRL. So that's the application part of this. Okay. So what we saw it, the two things. One is was the cavity is empty, but now we have a mode selected in the cavity such that it is under resonance, it is not in the resonance. So both the cases are discussed. Now what we like that, okay, we have the free cavity. Now if we can keep some field, that electromagnetic field light, okay, quantize inside the cavity, and that actually can couple to the atom. So let's start with a simple example like initial state considered to be any number state. Okay, so since it is quantized, so we will have that different quantization level that light can have. So light can be an excited state or ground state. So ground state, we saw there is no photon is there. So now we are considering any non-zero, means that non-zero in value. Okay, so that what would happen that now my state is initial state is in. So it is in excited state, but there is a availability that that one number state is there. Okay. So again, we can write in terms of the eigenstate of the total Hamiltonian, as we have seen. Okay, and ask that system to evolve in time. So once you ask the system evolve in time, we will get this expression. Okay, so that we have seen. Now here we can use some kind of tricks. Okay, tricks is that suppose we consider that the number state which you have chosen is very large. That means n value is very large. Okay, so that once we choose n value large, okay, keeping that pulse, okay, the pi by 2 pulse, so that we can integrate over a time period. Okay, the time period we are choosing here. Okay, so that omega 1 times t is pi by 2. And this omega 1, since it is the inner state, okay, so you know that it will be going by square root of n omega, which we have discussed in the last class. Okay, so why this is the factor is coming, okay, of the bare light frequency. So what you see that t is time taken to the atom, okay, so that it can the atom can move around this cavity. So the time which takes across the cavity, okay. So then what we can just do that assignment, okay, if you want to write in terms of this one, psi plus and psi minus, in terms of the uncoupled basis, that is Gn plus 1 and En, okay. So we will be able to write it considering that omega t is pi by 2. Okay, so if we just take the time period, okay, that capital small t is now is capital T is like that, then what we can put it here that omega t is pi by 2, then what would happen, sine omega t will be pi by 4. So sine pi by 4 will be 1 upon root 2. So you will get 1 upon root 2 as a prefactor, and again you will see that you will get something which is which you remember that it is like your so it is also in the resonant mode, delta is equal to 0. So like your maximally entangled states, which you discussed in the last class. Okay. So what would happen that you will get the Gn plus 1 plus En. So you will not be able to separate them out, that atomic part and the quantized electronic part separately. Okay. So that's why it is entangled. Okay. It is not factorizable, which we also discussed in the last class. Okay. So that is in the particular number state. But in practical, when you talk about the doing experiment, it is not possible to just get only one number state. Okay, so that is very, very impractical. So what is more practical to have a laser light, okay, which is quantized inside that. That means you are talking about semi-classical field, which actually you understood. Okay, laser lights as a semi-classical field, which also can be considered as a quantum mechanical quantized field. Okay, so once you have that, now initial state is now your E alpha. So alpha is the alpha t actually. Okay, so it is a time varying field. Okay, so which you can just evolve over time. Okay, now what would happen? You started with the E alpha. So alpha is linear combination of all the number states, as you understood. So we can just write them back as a linear combination of all the number state, okay, and we'll get this summation with the coefficient which is actually used in the alpha, okay. So once we have just written that one, what we will get that you remember that how this CN is behaving. So CN actually has the reconciliation, as you remember, with the CN minus 1, okay, with the factor of alpha. And you know that this is the relation which is satisfied because number of states are satisfying the Poisson's relations, okay. And if you just use all of them, what would happen that you are again able to write that system which was in the one of the state like E alpha. So your atom is an excited state, and you have one of the coherent state, okay, in the quantized mode, okay. So then what would happen that you ask them to evolve, and you will be able to write in this fashion. So once you write it, so this is all we know that from the way we have derived, we can write it in terms of the evolution, time evolution, unity time evolution of the eigenstate of a total Hamiltonian. Okay, so that psi plus and psi minus. Okay, and the p factor will be there. Now, what we can say that now we can just write this one in terms of the that uncoupled basis that Gn and En minus 1. Okay, again, you just putting this one, and so that with the sine cosine function which was there will come up already from the adding up these two terms, these two exponential terms, okay, subtracting these two exponential terms. Okay, so I would advise you those who are students, okay, just work it out, okay, as an assignment. So once you do that, what you can do that, we just take a simple approximation in the sense that when if we choose that in the square root of n which is there, because that this is summation over n, okay, this square root over n we can write, actually you can take it common, okay, and we can write in this fashion that so we can just binomially expand it, okay, so we write it so this is, as you see that if you just add them up, it is n comes up, and ultimately numerator will be n only, okay. So and this denominator will be cancelling out the outside factor, okay. So what you see that we just wrote it in such a way that here you have a get 1 plus 1 extra quantity, okay. So now depending upon this the numerator of the extra quantity, if it is smaller compared to the mean value, then this is a less than 1 quantity, and you can expand it, okay. So we are expanding it, okay, and saying that n is large, mean value is large, okay, and this is close to the n, then in that we can just stop the binomial expansion at the second term itself, okay, and then we can replace, okay, whatever we got it here, that square root of n by square root of mean value of n. Once we get square root of mean value of n, we can bring it out. So this is only possible when you are taking the alpha is large, okay. So that means you are asking that that number state to be dominated by a large value of n, okay. So once we got this expansion, what you see that we got this this factor sine function coming out from this one summation, okay. Here also cos function come out from the summation, and what you got it that inside this one. And now what you can show that this inside function is nothing but the time evolved the coherent state, that alpha. So what you could see that we are able to write, separate them out, okay, in terms of the atomic evolution of the atomic states, okay. And so this is between the ground and excited states, and the electromagnetic part is separated out. The cross product is there, and which is nothing but that time evolved state of the coherent state. So what you see that, so if you have a classical light, you see that semi-classical light, you will not get entangled anymore. Okay, so that what you have, that what you see it exactly that inside that cavity, that if you have a laser light, okay, you will be able to separate them out, okay, you will not be entangled over time, okay. So you have that separation between the light modes and the modes of the atoms, okay. So that's actually giving you the practical idea that how, okay, that if you have a particular semi-classical modes chosen in the cavity, okay, so what would happen, okay. And that is expected also, okay. So unless we have the particular number states, or if we just choose that totally vacuum, okay, it is very difficult to get entanglement at the later stage or evolved state. Okay. So, so here actually what is used here when you just put it, this one is alpha iomagnetic. I use the recurrence relation which we discussed earlier. Okay. So that Cn and Cn minus 1, I put it 1. Okay. That is at the level of the high n value, this is almost same. So once you understood that, so what we got it that in quasi-classical state evolved freely without feeling the presence of the atom. So it is actually independently working out, okay, the field. So it is not actually being perturbed by the atom, unlike that number state or vacuum state. Okay. So there is no more entanglement for large alpha. So this is very good when n is large, or alpha is large. What would happen when alpha is small? Certainly, we would like to know that when alpha is small, that means that the states, the coherent state is dominated by the lower n values. Okay. So now go back to that state which was written in gel for any value of alpha. Okay. So you would we could write that the states, evolved state in terms of the summation of n. Okay. And all the factors are inside summation, nothing is taken out. Okay. Now what would happen that if you want to try to find out that probability of finding that atom in excited state, and also a particular mode m, where m can be of summation. Okay, so what you will see that you will get a function like this one. There is a cosine function with a prefactor which will sum up. And what is happening? If you want to try to plot this probability, what you'll see that for a small value of alpha, let's say example 4, what you see that we see that Rabi oscillations what started, okay, initially at small t values, but slowly that Rabi oscillation will be damped after a few periods, okay, and eventually it disappeared with a minimum value of probability that is half. That means at this stage, okay, that you will get a state, okay, like entangled state, that state will be either in the ground state or a steady state. There's a combination of these two states. Okay, so you will have equal probability. But actually, it started with the oscillation, that Rabi oscillation. Okay. So it's slowly damped. Why it is damped? That's because, okay, so sorry, yeah. So as I said, the probability will be half after when it disappears. But why it is disappeared? That is because what we are doing that we are just superposing. The summation is there. Remember, superposing various sinusoidal model, which is little off phase, okay, between each other. Okay, so if there is a little off phase between each other, if you sum them up, okay, if you will see that flattening in the oscillation. That is what happening here. Okay, and but what would happen? The interesting thing is that after certain time, okay, you will see that again those summation which was taken place between the different modes, okay, they actually becoming again in phase. And what would happen? You get oscillation backs. Okay. So you get the Rabi oscillation back after a long time. Okay. So that in that if you just look at it in longer time scale. So what you saw that system actually decayed, okay, the oscillation decayed and revived. Okay. So what you can say that this because of the phases of the different modes are coming in tuned up. Okay. So what would happen? The oscillation come up and you got the quantum revival. So this is known as quantum revival. So you get Rabi oscillation again. Okay. So that's the beauty of this one. So, and what you saw that these two phenomena, the damping and this the quantum revival, this was not present in the case of classical theory. Okay, classical theory really actually decays down. Okay, so it just in a free space it will be just going down that probability. And here this is a purely quantum phenomena which you are looking at. That there is a not only Rabi oscillation, we are having some kind of a damping and revival. So this is a very, very interesting phenomena which can be used, okay, different experiments. So I believe that you got some idea now So when you can interact the matter, here the quantum matter we are talking about. Earlier it has been discussed that quantum matter can interact with the classical light and it could explain many things. Now we see that now the quantum matter are interacting with the quantum light, the quantized light. And you see that different kind of effects, which we just said very naively, or some of the elementary things we have discussed, and it has been explored further in many times in many experiments and doing the different technology out of this. Okay. So I want to stop here this one, okay, that interaction part, but I want to just get in some things which I promised, but I will not be able to do much of this, okay. Like one of the things, some of the things which I proposed in the article when I talked about, okay, I'll be able to discuss. So let's take one of them, which is very interesting. And if there is a question on these things, which I'll try to address at the end of this discussion. So that is that one of the famous things, that two-photon transitions. Okay. So one of the example which is very popular, as you know, that Raman transition is a two-photon transitions. What happens that in the Raman transitions, the people use in the vibration levels. Okay. So either you can have the infrared absorption and go from one vibration level to another vibration level, or you can shine that the light, okay, from the one vibration level which can go to the any excited levels, okay, which can be virtual state, okay, and shine another light, okay, bring back to that state. If you are bringing back to the initial state, that is nothing but your Rayleigh scattering, okay. But if you are bringing back to, because it is stimulated emission, but to the other states, either it will be a Stokes or anti-Stokes, depending upon whether you are bringing to the lower level or higher level, okay. So you will get the Stokes and Stokes. Advantage, a lot of advantage of having the two-photon transitions. Okay, so what is most advantage is that to have the laser, to use the laser which is mostly available like optical laser. So you can have the optical lasers, okay, which you can use it for this experiment. Okay, so unless that infrared lasers which actually used for taking from one level to another vibration level. So if you just look at the, this is taken from Wikipedia. So there is a how the beam splitter is used to do this kind of experiment is explained there. So I will just advise you, okay, look at also the experiment, okay, which will be very interesting. Okay, so I'll not be able to spend much time, but I want to just give some flavor of this. Okay, so what would happen that if in the case of the quantum technologies, okay, apart from this kind of transition between the vibration level, okay, when you talked about the in terms of atoms, okay, we can use this two-photon transition, okay, to take atom from one hyperfine level to another hyperfine level. As you remember in initially one class before, okay, so we have discussed about the hyperfine level. So that you have the one of the standards, the rubidium, okay, you can have hyperfine ground state F equal to 1, F equal to 2. Similarly, excited state, okay, you can have F equal to 1 and 2. So this is 87 rubidium, okay, which is hyperfine states are separated nicely, okay, at the ground level. Now, what we can do, take like these cases, we can take electron from one state to another state using that two-photon transitions. Okay. So just look at this particular picture, forget about the 2p3f, and let's see that if we just concentrate on this one, okay. And here, if we have, we know that for each of the states, the hyperfine F equal to 1, F equal to 2, or excited 5p3 by 2, F equal to half, F equal to 1, F equal to 2. Okay, these are the intrinsic level. Okay, and here if you talk about this component, okay, components are like you can just have the depending upon the F value, you can have +1, -1, 0. Similarly, you can have for 2 equal to -2, -1, 0, +1, +2 also there. Similarly for excited state, these are designed. Unless you apply magnetic field, okay, you will not be able to separate them out. And this is external magnetic field, remember, okay. So once we have external magnetic field, we can separate. Now our application which we look for, that we want to take, okay, the atom, okay, which is in a mixture of the any of this hyperfine level, okay, because if you see them generally without magnetic field. Those are mixed up in the different hyperfine from one hyperfine sublevel to the another hyperfine sublevel. If we can bring it, okay, that's using the two-photon transitions. Okay, so here actually we are just looking for the particular this F equal to 1 to F equal to 1 in the p half level. Okay, so that's transitions. So and what we are doing, we are using the two-photon transitions. Okay, or two-photon excitations. Okay, so let's look at it. Uh, let's say again that A sub and P hub levels, okay, and we are interested to bring from one. This is not a Rayleigh scattering. This is from the either Stokes or anti-Stokes. Okay, so it's like a Stokes, so going from the one level to the another level which is higher in energy. Okay, so here the most important part, okay, if you just shine the light, okay, from one of the photon from one of the ground state to the level of the one of the eigenstate of the atom, the hyperfine eigenstate, what would happen, that atom will go to the excited state and spontaneously decay, and then you will not have any control on the atom to bring down this one, because it can decay down to the any of the lower level. Okay, there's a probability, every probability is same. Okay, and depending upon that, certainly the transition strength. Okay, so what is done? It is done that so will not shine the light exactly resonant to the resonance transition frequency. What we'll do, either we'll just shine it little lower, okay, so it will be red detune, or it will be little larger in frequency, so it will blue detune. And that actually it can be defined, that energy separation can be defined with the detuning frequency. Okay, so if we just shine it, then if we shine another light, another photon, okay, to bring that atom to the particular state, depending our own choice. So important is that here we are choosing our own destiny, okay, by using the another light, another photon, okay, and which is like a guided missile, okay. So you are bringing it to the particular level, okay, unlike the spontaneous emission. Okay. So here the way we can do that same interaction one which you have done, but only thing is that here you have availability of two photons. So that you have to have E1 and E2 are two photon, your dipole transition. Here you have the propagation terms, okay, for each electric field. It is in the forward moving, backward moving propagations, all the terms you write. So in the Hamiltonian, you have full things. And if you write it, I am not going to discuss in detail. If you want, I can send you that write-up. Okay, so what you can find out, the transition frequency here, it depends upon the transition frequency of transition probabilities. This is transition probabilities depends upon transition probability of each individual photon due to each individual photons. Okay, that is 1 and 2. Okay, and it also depends upon the detuning in a frequency, that is delta, which we have discussed in the last few slides also. That same kind of a delta detuning part is there. Now you see that corresponding to the delta value, whether small or large, we can just make the coupling stronger and weaker. Okay, so if you choose that the delta is large, that means that these values will become smaller. That means what would happen? You choose that where actually this atom will be taken to the virtual state, and the virtual state will be very lower in energy level compared to the resonant length. Okay, so then it will be, you see that this coupling will be very weak. But if you just choose it very close to the resonant excited line, okay, then what would happen? That you will get very strong coupling, okay, or strong tension probability. Okay, so to get that, you will have that, choose that delta is very small. So what is the application of this? This is the one which I want to demonstrate the application part. Okay, so this is known as optical pumping. You might have heard this. So this one, the picture is taken from this quantum optics group in LMU, Ludwig Max Planck University in Munich. Okay, so where actually they have shown that that you can have a, like, you can think about a balloon. Okay, you purchase from this market rubidium gas inside a balloon, and when you purchase them, what would happen? That this atom will have particular isotopes. That's all they'll tell. But it will have a mixture of all this kind of hyperfine level, F equal to 1, F equal to 2. Okay, also it's all the degenerate, the sub-levels, hyperfine sub-levels. Now, to do the experiment in future for the what actually intended to that, like a laser cooling trapping, which we will not be able to discuss. What do you want? You want all the atom to be a particular sub-level, okay, so that you can have better control on this. So we need actually high precision, like an atomic clock. We need a particular hyperfine sub-levels to be actually pulled down. Okay, this is the atom. So we need that whatever atom we are choosing, okay, that so that will be in a particular state. For that, optical pumping is one of the ideal technique. Okay. So what it does actually, India designs, but once you apply magnetic field, okay, what would happen? These designs will break down, and you will get the separation between these three sub levels. Okay, so there will be -1 going down, +1 go up, and 0 will be unaltered. Okay. So once we apply this magnetic field, we will have these sub levels. Okay, and magnetic field is required for laser cooling. So that means that you will be a hodgepodge of different energy levels, and you will not be able to control the system at that, because as you have seen the number of state cases, okay, it is mixed up number of states. Okay, here also mixed up different energy levels. You have no control on the systems. So you want to make it in the particular levels. Okay, and these splittings actually, as you know, that hyperfine splittings, okay, can be understood in terms of the magnetic field. It goes to linear to magnetic field here. Okay, it can go quadratic also. So we are just sticking to that, and depends upon that your hyperfine quantum levels and your hyperfine coupling terms is GF and more magnetrons. Okay. So what is our goal? Goal is to bring all the atoms in the same hyperfine sub-levels, okay, of the ground state. So that is our goal here. So for that, what we do? Okay, so let's say that we have a two-level systems. Okay, the S up and P half. Okay, so all the atoms which you got it in the S up in the ground state. Okay, from the market, and we have this balloon here. Okay, and what would happen now? We apply a magnetic field. Now there will be one person who has because this magnetic field is using the Helmholtz coil. Okay, so from the both top and bottom, you put the Helmholtz coil and around this balloon. And what would happen that you can now control this coil current through the coil and control the magnetic field. So there will be one person who can control this magnetic field. So he will tune the magnetic field. Okay, and so by just changing the current, or so anyhow, number of loops are fixed here. Let's say, and so kind you just push it a different kind and change the magnetic field. So his work is the boy's work is that to change that magnetic field. Then what we do that we shine the lights. Okay, these lights, okay, the laser lights which you are shining, that has a breadth. Okay, that with is the light is that, so that any kind of transition from any of the hyperfine sublevel to the steady state it can go. So that from F equal to 1 to F equal to 1 of P half level it can go. So that with it has. Okay, so that's important that you can have all the possibility of all the transitions. Then there will be one lady, okay, one girl who actually will try to observe this. What is happening? Once these guys changing the magnetic field, what is going on? And that's what will do that. That lady will try to plot, okay, depending upon how the boy is changing magnetic field and what she observes. So she will try to plot something, and that will give the physics. And that can be demonstrated in the lab, which I'll not be able to complete today. Okay. But maybe in future, if I get time, I'll discuss. But let us understand how these things, how this protocol works, okay? So that how this new physics can become and how all the atoms can be brought in the particular hyperfine sublevel. So for that, let us just look at the hyperfine sublevel once again, okay, for these two state A sub and P half, okay? Now, we just shine the light, which is a particular, let's say, that it's a right circular pulse, right? That is sigma -1. That sigma values, spin values plus minus. Okay, that means right circular pulse. So that means that it will just pump the angular momentum to the systems. Okay, and it will just whatever angular momentum is there. If the electron get excited, its actually angular momentum will be reduced by 1 because it is sigma minus. Okay, so what is allowed transition? So you can have selection rules. So what would happen that MF value equal to 0 if you think about the atom is available at MF equal to 0. And as you know that there's a with of this the bandwidth of this light has such that it can take the any of the hyperfine sublevel to another hyperfine sublevel of the excited state, so that we will be able to get this kind of transition, okay, depending upon the selection rule allows. Okay, so the sigma minus is allowed means that from MF equal to 0, you can go to the MF equal to -1. Similarly, what happens that you just try to see the MF equal to 0 to MF equal to 0, that's not possible. So that's why the red color. Red color means that that is not possible, and blue color means that is allowed. Okay, and if you that means that so you are allowed to go from MF equal to 0 to only MF equal to -1. There is no other possibility from MF equal to 0. Similarly, if you want from MF equal to 0 to MF equal to +1, that is not possible. Okay, because sigma minus is there. Okay, and it has only spin restriction. After spin is actually 1, so you can. Similarly, if you go for if MF equal to +1, so this is also not allowed as selection rule. But what would happen? MF equal to +1 to MF equal to 0 is allowed. Whereas that this from MF equal to +1 to MF equal to -1 is not allowed. So what would happen among this MF equal to 0 and MF equal to +1? Okay, also we have only 2 allowed transitions are there, and those who are MF equal to -1, okay, so they can't actually see this light, okay, because there is no scope to go anywhere. But if it is already MF equal to -1, you can't bring down the level to MF equal to -2. That state is not available. Okay, so since that state is not available, for this case, this light is like a nothing is there, so no one is coming. So it's actually light will pass through for if you have this one. So ultimately, what would happen that you can say that for absorption, you have only allowed one MF equal to 0 to MF equal to -1, okay, and MF equal to +1 to MF equal to 0. That's what allowed. Okay. So what about that once it goes to the excited state? Now see here, there is no detuning I'm talking about. Here it's actually we are allowing to go to the exactly in the excited state, and we expect them to spontaneously decay. So when it is spontaneously decay, okay, it can decay to any light. It can have the decaying to sigma plus or sigma minus or sigma 0. Okay, so sigma 0 also can be written in terms of sigma minus, sigma plus. Okay, so what would happen that you will have that all different tension possible, but only thing is that -1 can't go to the +1. Okay, or +1 can't go to the -1. Okay, so that the two angular momentum change is not possible. So what would happen? You have that -1 can go to the -1, -1 go to the 0. That is spontaneous emission. And so, but this spontaneous emission, okay, since this is going, since that transition is staying, because this is between hyperfine level, only that is a factor, okay, hyperfine factor, which is actually between hyperfine sublevel is same. Okay, so that probability to come down to the MF equal to -1 and MF equal to 0 is 50-50 from this MF equal to -1 level. So that what would happen that there is a 50-50 probability that this photon will be emitted and this photon will be emitted. Okay. Similarly, if you see that from the MF equal to 0, there is a 50-50 probability that it can go to the MF equal to -1 and MF equal to +1, because 0 to 0 transition is not allowed in terms of the electromagnetic transition. Okay. So what you see that when they are coming out, you have to just observe it. Okay, that we have that atoms which are MF equal to -1, MF equal to 0, MF equal to +1. So atoms which are there in MF equal to -1, they are just unaffected by this light. MF equal to 0, they got excited and go to the MF equal to -1. And when they come back, okay, they come back either in MF equal to -1 again. So it is coming back to the state where already some atoms were there, and some of the atoms are going to the MF equal to 0. So that's 50-50 probability. And from MF equal to 0, it can comes to the MF equal to -1 and +1. These are 50-50 probabilities. So what would happen if you see that in terms of number of photons? So if let's say that you are starting the 100 number of photons, and they are for the market when you got it, they are in terms of the 30-40 number of MF equal to -1, MF equal to 0, MF equal to +1. So that 30 number of atoms which are in MF equal to -1, 30 are in MF equal to 0, 40 are there in MF equal to +1. So these 30 which are there in MF equal to -1, they are unaltered by this or unaffected by this light. Okay, but what would happen that when you these others too, actually MF equal to 0 and MF equal to +1, they will be affected. And but when they will be affected, they go to excited state, and when they come back, okay, because of this in the first cycle, when the laser comes, okay, so what would happen that let's say that only tension probability is such that there are only 10 number of atoms excited from the MF equal to 0. So what would happen if MF equal to 0, only 10 number of atom goes, so out of the 30, okay, only the 10 goes and to the excited state. And then when they come back, what would happen? 5 of them go to the MF equal to -1, 5 of them comes to MF equal to 0. So what would happen that already MF equal to -1 had 30, now additional 5 is gone to that. And these, whatever they are going to MF equal to -1, they are unaffected by this light. So they will be there for a long time. So they are not perturbed by this light. Only things which are coming back to the MF equal to 0, again they'll see that lights which are coming following that. Okay. So what would happen, and that what would happen to that similar thing happen from MF equal to 0, which are coming back. So we'll have additional 5 electron, okay, which will come to the MF equal to 1, and there are 5 on which will come to the MF plus 1. So ultimately, what you see that MF equal to -1 has gained some number of atoms. That is, they had a 30, additional 5 they got it MF equal to -1, and 5 they got it from MF equal to 0. So ultimately they got 40. Okay, so from 30 they got 40, whereas this MF equal to 0, they are just reduced by number of atoms, 30 to 25, 40 to 35. Okay, and if you just allow this to go through the some cycle over time period, what you will see that all the atoms will go to the excited state, that is MF equal to -1. So it will be in ground state, but it will be going to the MF equal to -1. So what you see that over time, what you see that most of the atoms will go to the state, okay, is MF equal to -1, or you can say almost all of them. So what you can calculate that how many cycles you require. That is easy, because if you just go through this one, you can calculate easily the how many cycles you require to take all the atoms to the state MF equal to 1, MF equal to -1. That is easy to calculate. So once you calculate that one, what would happen that once all the atoms goes to that MF equal to -1 of F equal to 1 and ground state, okay, so light will not be absorbed anymore. So if you just want to plot that light observed by this lady, okay, if you see that this lady has a detector which is observing or detecting the number of photons are coming, okay, initially what would happen that almost all the lights are being absorbed by this atom, but slowly over time, what would happen that she will get that scenario that where this she gets all the lights back. Okay, that means so absorption is 0, and you will see that all the lights are back. So she will get full lights back. Okay, through the medium. So again, it is through the medium. So the lights are passing through the medium, but it is not being absorbed. Okay, so that is the observation. So what she will make. Okay, and for her, what she would see that the medium will be transparent for the sigma minus light which she was using. Okay, and she was using that frequency close to the resonance frequency between these two. So you remember that. So that that condition is possible. So this is like a thing that you have a system which was opaque to the light. Now you are making the system which is transparent to the light. So that this transparency is using electromagnetic field and light. Okay, so this is known as also called electromagnetically induced transparency. So this is one of the approach which has been used, okay, for laser cooling and trapping, okay, to bring the atoms in a particular level. So I am not able to go further how to demonstrate in the lab. Okay, so that will be ideal to show it. Okay, so I am just already shooting the time. Okay, so I have to close this some of the techniques which are very novel to get the ultra cold atoms like laser cooling. After doing this optical pumping, you can have this magneto-optical trap. Okay, which can be pull down the systems, okay, atoms to a microkelvin level. And to go further, okay, so one of the novel technique which have been used, but very naive but novel technique, which is known as evaporative cooling, to bring down to the some few hundreds of nanokelvin where Bose-Einstein condensation is observed. Okay, if time would be there, I would like to discuss those things. Maybe in future, if I get time, I will discuss definitely. So far, so I would like to conclude this course by that. So I was promised that I will cover it, but I could cover only these 6 particles. Okay, so up to that. So no, not 6. I have completed 8 of them. Okay, so that this 2 also is covered now today. Okay, so we have cavity quantum electrodynamics, 2-photon excitation. I have just talked about a little bit, though I didn't show the calculations, which will be ideal to understand the physics of that. And the application part of 2-photon transition as optical pumping, which has briefly showed the protocol. What was left is this one. Maybe in future, if I get time, I'll try to discuss. So I believe that in this last 10 classes, I could share some of the things. I gained a lot, but I could share some of the ideas of this quantum optics with you. Okay, and maybe we mutually gain something. So at least I got again a lot of things. Okay, by discussing this one, and I would like to thank all of you to take part in this classes. Okay, and be attentive and work out in the tutorials. I would like to conclude by thank you once again from my bottom of the heart, and thanks for this attention. Thank you. Over to you.
Yeah, thank you very much, Professor Sanjay. So there are a few questions on the chat box.
Okay.
Yeah. So the first one is by Mr. Asif Barik. So if the photon doesn't enter the cavity, is it though time delayed by the cavity?
Repeat it also. Is the last part I didn't hear?
Yeah, I think the question is not very clear. So can Mr. Asif unmute himself and ask? So yeah. The question in the text box is, if the photon doesn't enter the cavity, maybe is it time delayed by the cavity?
No. The cavity is made that it is totally sealed. Okay. So no photon is coming out. No photon is coming. So it is like a that you have making it such that okay that it is black box kind of things. Okay. So whatever there inside there. So that you are not allowing anything go out. You are allowing anything to come in. So what I discussed actually, it is pre-planned. Okay, either you keep the atom in excited state. Okay, so you are bringing the atom from outside and putting it inside the cavity excited state, where cavity was empty, which was very unlikely. Okay, if there is some electronic field or light is there, okay, that I know that because of the confinement, okay, the light is quantized, and because of the confinement, okay, since it is quantized, okay, how that present confined or quantized light interact with the excited atom, that was discussed. Okay, so it is not that from outside anything we are bringing. It is whatever there inside the cavity. Okay, we discussed. Okay, so for contacting the outside light, okay, you may have to make a hole, and that actually you will be treating as like a bath. Okay, so that has to be treated differently. Okay, so you can have an exchange between that bath and your cavity. Okay, so that has to be done. So that is a decoherence will come in picture. Okay, so I'm not going in details of that, but that will take some other direction to the discussion.
Okay, so there are a couple of questions from Dr. David Joseph. So the first question is, rubidium is commonly used. The resonant frequency is 795 nanometers, available with titanium sapphire laser. Is there any other resonant atoms, atom laser pairs?
Yeah, there are a lot of. So rubidium is used in optical. Then cesium also is used. Okay, ytterbium is used. There are many nowadays. Many of them are available in optical lesions laser. Okay, and so they are being used for that. So all of them actually used for atomic clock. Okay, so if you just look at the number of species, okay, used in the atomic clock, you will see that. Okay, so mostly of them are in the optical. There are few of them available in the microwave length. Okay, so the recent experiment 2020, what is actually done using a 2-photon transition for optical clock, and that is the one of the novel technique in the sense that when you have 2 photon, you will actually be able to make it Doppler free in the sense that you are shining both the photon from counter propagation direction. Okay, so whatever that momentum pumped to the atom by one of the photon will be compensated or will be nullified by the other photon. And you will make that system will be Doppler free, or the atom is Doppler free. That's a very advantageous, okay, to have the atomic clock in the two photon cells. And that has been done in, I think, 2019 or 18. And recently there have been some other work. So that was a PRL paper. So there are many of the atoms, many atoms available, okay, which are in the optical region.
So the other question is, only hyperfine levels are useful for this cooling, or any other energy levels can be used?
So the thing is that, as I say, okay, I think you understood. So whatever level is there, we are looking for, okay, that depending upon what precision we are looking at. Here, when you are talking about atomic clock or quantum computing, okay, what you are doing actually, we are looking at the precise level, okay. And you remember that in atomic clock, the level we are talking about, the precision is observer 10 to the minus 19 of 1 second, okay. So if you look for that kind of precision, okay, you should have the precision between the energy levels is that accurate. And for that, okay, for given a isotope, okay, given isotope, you should see that at that level, okay, if you have a light of that very narrow bandwidth, okay, what are the transition possible, okay, what you can see, okay, they are actually, you have to go in the hyperfine level, okay, and see that the difference between the two hyperfine levels, okay. If you have a, if you are not interested about the high resolution, if you are something like you have a brown band light, okay, then you could just satisfy yourself with the finer structure level, okay. But the thing is that that is the old jamana, and now in this new one, okay, over the last few decades, okay, people are talking about the high precision experiment, and there you require them at the hyperfine level.
Okay, so the next question is from Mr. Sundar. So the question is, can you please send us a paper and other info on the latest two-photon atomic clock?
Okay,
Does
I'll
it involve quantum
CAMOST
entanglement?
website.
Yeah. So does it involve quantum entanglement?
They want a quantum entanglement also.
Yeah, no. So he wants this paper on this latest two-photon atomic clock. And does this process involve quantum entanglement?
Yeah. Okay. So all those things will be there.
Okay. Yeah, so these are all the questions we have on the chat box. Any other questions? I think the participants can unmute themselves and ask. As this is the last lecture, maybe you could even ask some questions from the previous ones if you have.
Vinay, I'm not sure if they can unmute themselves. I think the host
okay.
has to, I think the host will have to unmute them.
Okay, okay. Or maybe you could type on the chat box that you want to ask a question.
Yes, or if they raise their hand, maybe the host can unmute them.
Okay, looks like there are no further comments or questions.
So they can ask in the mail, or they can attend a tutorial class, which will be there in today.
Yes, today there's it. Okay, so then over to you, sir, Deshmukh sir.
Yeah, thank you. Thank you very much, Vinay. This has been a very exciting lecture series. And Sanjay, we are very grateful to you, the whole Center for Atomic Molecular Optical Sciences and Technologies, and all the participants on behalf of the IIT Tirupati and the ISER Tirupati. We are all extremely grateful to you, Sanjay, for spending your time. It has been a huge success, I would say, and I must congratulate you for such a wonderful lecture series. One comment I might add to this, especially because the center is based in Tirupati, I'm reminded of the visit to Tirupati by Professor Serge Harosh, who, along with David Wineland, got the Nobel Prize in 2012 for the experimental realization of the Jaynes-Cummings model, which you
Yeah,
discussed.
I discussed
Uh,
last class that about his
yes,
contributions. Okay.
yes. So this was such an important piece of work, and it was wonderful to have him in Tirupati. And I think students and faculty of both IIT Tirupati and IISER Tirupati were very privileged to meet him. Subsequently, we had the technical cultural event at IIT Tirupati. It is called as Tirutsava, right, Vinay?
Yes.
So Professor Harosh also gave a talk in Tirutsava. It was in a video conference. We could not have him personally, but it was a wonderful visit. So very nice that Sanjay elaborated on this and brought up the participants to frontier research in the field of atomic clocks. I think this is an amazing course. In 10 lectures, starting out from the very basics, Sanjay has brought all of us right to the frontiers of research in atomic clocks, Bose-Einstein condensation, and many of these techniques are an integral part of the research in this field. So thanks to Sanjay, thanks to the whole team, uh, everybody who handled the question answer sessions, to the technical team. Vinay, I think we are ready to close the session with
I would like to
Sanjay.
just say that thank you. So it is a great it was a good journey for me also. So I have learned a lot of things. I have gone to the deep in some of things where actually some of the basics are clear to me also. Okay, and it is nice to interact with all of you, share things, and it's a really, really good event which I would like to mention. Thank you.
So we can close the session, but let me just warn Sanjay that he should expect a phone call from me to requesting him to give some more lectures sometime in the near future, or
Yeah, and
whenever
maybe
it
in the
is
future time.
whenever it is convenient to him, because I think this is something which certainly must continue. So thank you all very much. Vinay?
Yeah, thank you, sir. So we can close the session.
Yes. Okay. All right, Sanjay. And goodbye, everybody. You will, of course, meet for the tutorial.